Hi, everybody. Dermot O'Shea here. I'm the host of the Antenna Podcast. Welcome to another episode. Today, I'm delighted to introduce our new guest, Gabriel Rebeiz. Gabriel, would you like to give us a formal introduction?
Hi, Dermot. How are you? Thanks for inviting me. I'm a professor at UCSD, University of California, San Diego. So you are my neighbor in San Diego, and good to see you. And I have been here since 2005, January 2005, which is 21 years. Before that, I was at University of Michigan, Ann Arbor, Michigan, which is also a great university, and was there from, I would say, effectively January 89 to December 2004, so 15 years. So all in all, I've been a professor for 36 years now, doing antennas and millimeter waves and circuits and all of the good stuff that makes us happy.
Yeah, and how did you get into antennas in the first place? Like, is it something yeah, what first was your
Well,
first?
I got into antennas like every graduate students. I took a class. I went to Caltech. I graduated from the American University of Beirut, and I was doing circuits. And I went to Caltech trying to do circuits. You know, high frequency circuits was starting to get there. Microwave was starting to get there, but, it was gallium arsenide and it was circuits, and power electronics was starting to get there. There was Professor Middlebrook giving a phenomenal circuits class and, power electronics. And there was Bill Bridges and Dave Rutledge. And I joined the circuits group. But I took a class in advanced electromagnetics with Bill Bridges, which was electromagnetics and optics. And I got hooked onto it. So I went to Dave Rutledge and I said, "Hey, Dave, I want to work with you." And he said, "Well, take an antenna class." Well, there was no antenna class. So I picked up books. I picked up Elliot, Professor Elliott's book from UCLA, and it was a phenomenal book. It was amazing. I mean, you needed some math to know his stuff. Bob Elliott is not an easy book, but it is so well written, so beautifully written. I got hooked onto it. And then I went to Dave and I said, "I want to work with you." And he said, "Okay, I'll accept you." And that's how I got into it.
Very good. So you went from Caltech and then to Michigan after that, was it?
Yes, Caltech to Michigan and then Michigan to UCSD. Yeah.
Gotcha. Yeah, you realize the weather's better down here in San Diego than Michigan.
Yes.
Sure.
Yes.
And so and so your classes at UCSD today are you teaching antenna classes, or there's more variety to
No,
it?
I teach an antenna class every year, and you should
Okay.
ask your people to come and join. We teach two antenna classes. Well, we teach a series of antenna classes. The first one is undergraduate antennas, typically taught by Dan Seaman Piper, EC 123, and then I teach 222A, which is antennas at the graduate level, and we cover all antennas, even up to reflector antennas. Then we teach advanced electromagnetics and numerical techniques by, Vitaly Lomakin and others. Then we teach advanced antennas at the end, where we do reflectors and phase arrays and Floquet modes and impedance surfaces and all of the stuff. So by the time you finish UCSD, you really know your stuff.
I like it.
Really know your stuff. I mean, you've taken 4 quarters of advanced EM and antennas and numerical techniques. You know how to analyze stuff very well.
Great. And where do the graduates end up then? Do they normally go to like defense and aerospace defense companies, or is it varied?
Most of them end up at commercial companies. Apple is a big hirer of our team. Qualcomm hires a lot. Who else? I mean, some of them are at Amazon Kuiper. Some of them are interviewing now at Starlink. Of course, some of them will go to Hughes Research Labs and to Raytheon and others. But I would say most will end up commercial.
Yeah. So
Yeah.
yeah, we kind of compete with some of those guys ourselves. Like they like, you know, people that have worked in a company like Hourglass as well, because they know they're trained on it. A lot of those guys tell me, there's not enough students going into this area anymore. That most students are focused on software, AI, and that type of stuff and
Hmm.
coding. Um, but to me, there seems to be like unbelievable opportunities in this area. Have you seen it decline or steady? Like, what's the kind of trend on
I, I, I
students?
I fully agree with you. I actually tell my students that if you know RF microwaves as parameters and circuit design and RF systems, if you know antennas, you will never retire in your life. I mean, so many antenna people, after they retire, they drag them back in. It is still a black magic art. Okay, you can automate to design a simple microchip antenna, but put this antenna in a structure, in a wing, in this and that, and so on, and you need experience. You need a lot of experience to design it. Put it in a box, put it in a TV, put it in a computer, for God's sake, put it there in this wireless LAN, and you cannot just use any standard antenna. So other than the defense, even on the commercial side, like Apple has whatever 8 to 10 antennas now, and they have tuners in them, 14 tuners in them, and Samsung. Also the same thing. You end up with a lot of work on antennas, a work that cannot necessarily be automated, and it's highly based on experience and know-how. And in my opinion, yes, not enough students choose this because, as you know, it's mathematically hard at the beginning, even though there are tools just to understand it, and it's challenging. But once you master it, there are very few, and you will have a job for life, basically.
Yeah. Yeah, no,
Yeah.
we find it hard as well. There's a lot of candidates in India and Taiwan and China, but not many candidates in Europe or the United States. So it's
Yeah.
kind of been like that in the last 10 years.
Yeah, don't get me into it. That's a whole different podcast about our educational system and
There goes.
how poorly trained are some of our U.S. graduates in math skills. That's a whole different podcast.
Yeah, I know. I have
And
3 kids in high school in California.
yeah,
We could do a whole podcast on that.
yeah, a whole podcast on this, and it will all be complained. It will all be complained. So let's stick on something nice here. Yes.
Okay. Well, then talk to us about something then interesting, like what you've worked on so many projects, both in the university setting and I know in the commercial arena or for the commercial space as well. Any project that you're particularly proud of or you found really interesting that you could talk to us about and what the application was?
Yeah, you asked me this question. I was thinking about it, and times change, and we worked on different things. And at the beginning, we were working on terahertz antennas, and you can see my papers. I have a paper referenced to whatever 1,000 times, which is a summary of terahertz antennas. And we really didn't understand anything about terahertz antennas, and that was like 1991, 1990. And we worked a lot on it, and we actually, by the time we finished, and that of course started with Dave Rutledge, by the time we finished the silicon lens and we finished the antennas on membranes and we finished a lot of this family of antennas for terahertz, double slot antennas with Jonas Mudzinas and the lenses, and Dan Filipovich analyzed the lens in my group, and Walid Ali Ahmed and Steve Gerhardt and so on did a lot of these double dipoles and integrated horns, and George Elefteliadis. All of these guys, by the time we finished that, we really understood terahertz antenna as well. And after that, I went more towards circuits. I kind of abandoned antennas for about 8 to 10 years, and I went into MEMS, and we developed a lot of MEMS switches and phase shifters, then went into RFICs, where we developed, with Tim Hancock, with the first SIGI phase shifter at KU band 4, KU band SATCOM. And then Kwon Jin Go came, and a whole set of students came where we developed the highly integrated SIGI BFIX, which we call beamformer ICs, which I would say all the beamformer ICs used today Genesis came from our group for SATCOM and for radars. We did them way before anybody else. But then once we had the beamformer ICs, we went back into antennas to build millimeter wave antenna arrays and wideband antenna arrays and SATCOM antenna arrays and radar antenna arrays and automotive radar antenna arrays, because we developed BFIX for automotive radars too. So kind of it started with terahertz, and then I kind of abandoned antennas for 10, 15 years, became an MTT person, and then went into active antennas, which is basically phase arrays for automotive radars and SATCOM and general purpose 5G communications and other things. So it has been a lot of different projects and a lot of different frequencies. Yeah.
And what's your favorite, though? Is there anything that you really go, I love that, one that we can
It's
be
a tough
proud of?
question, because you're asking, what's your favorite child? I mean, it's let's say you have 8 children. I mean, which one is your favorite child? It's very tough to answer such a question. I mean, it's impossible to answer such a question. So the answer is that every set of students or every set of projects had different challenges. In the at the beginning, in the terahertz, we really needed to understand it, and Filipovich really did a phenomenal job of understanding how the dielectric lens worked from numerical techniques, and was a double slot feed. Eleftheriadis and Ali Ahmad and others did a phenomenal job on the integrated horns and on the making very, very high efficiency radio astronomy type antennas at millimeter wave frequencies with Schottky diode detectors and receivers and so on. Then as I said, we kind of stopped, and then we took it back again. Jen Edwards came, did a very nice job on the sinuous antennas and wideband spiral sinuous antennas, and then we kind of left it and then started doing the phase arrays. And the phase arrays, the first one was, we were the first, way before anyone else, to do 5G millimeter wave full planar phase arrays on a single PCB, with antennas on one side and chips on the other. And that was Karim Kibaroglu with Mustafa Saginer, and
when was that? Because when you said the first one,
that was 2017.
Okay, so
that was before 5G.
Because I remember Verizon and I think AT&T bought some spectrum in like a 28 gigahertz, 29 gigahertz, and we worked on some arrays as well, and very, very complicated, right? You need a lot of patience. The materials were quite, I remember one of the issues that they had was all the materials are quite expensive. The connectors, the PCBs, the cables, etc. So to implement it from a commercial perspective for 5G in all devices was going to cause issues.
Well, that's why I feel we did something that's revolutionary there, because what we did is we integrated the chips with the antennas on a low-cost substrate, which was Mectron 6. And actually, we really did not know anything about fabrication there. It was Keysight, the Keysight Santa Rosa team, with Mark Pierpoint and his team there, who were also doing 5G. And they are the one who helped us at the beginning learn the PCB design techniques and learn how to assemble these chips. And at the beginning, the first arrays were assembled by hand. They didn't even send them to, normal. The first arrays, like, 64 element arrays. Well, let's put 8 chips, each one, feeding, 2 by 2 arrays and things like that. And let us assemble them by hand. So we learned a lot as we were going through. We had a very nice relationship with Keysight, and they used them, for their instrumentation. But definitely, I mean, when you look at the record, we were the first who said the only way to do it is to do it this way, and put a filter and to put a mixer and put it all together. That was in 5G. Before that, we were doing SATCOM. So you tell me what's the most interesting project? Well, again, an interesting project would be that I spent about 6 years at Lockwood Collins in Cedar Rapids, Iowa, building the first SATCOM arrays, way before Starlink, and building the first weather radars, way before anybody else. And they called me in. We designed the chips internally. We designed the PCBs internally at Rockwell Collins. They gave me full access. It was wonderful. That's Bob Newgard and Lee Paulson, Michael Hageman, the whole team there. And I was embedded into the team, and I would go there, fly every month to visit Rockwell Collins. And I learned from them, and I saw from them how you build a product from beginning to end. And I still thank them for this experience, because you realize it's not the antenna team, it's the RFIC team and the antenna team and the packaging team and the thermal team and the software team and the testing team, and everything together. You put it all together to make a product.
Yeah.
And by 2013, 14, we already had SATCOM systems and weather radars working at Rockwell Collins, even before that. And they were published. Some of them were published at the Phase Array Symposium.
Yeah.
But at the university, these were very large arrays. It could not be done at the university. At the university, we went into automotive radars because they were small, and we designed chips, and they were small arrays. But at the university, it was not till 2017 until we started building 256 element arrays, and 4 by 8 by 8 for single and dual pole for 5G MIMO, 5G, polarization MIMO. But the first large demonstration of phased arrays that at least I did was in the 2000, maybe 2010 to 2014 area with Rockwell Collins.
Okay.
Yeah.
Interesting. Yeah, that was early days, and I love what you said there about the whole, team, all the different teams you need to bring an antenna from concept to production. Like mechanical engineering, we have to do a lot of mechanical engineering. In some jobs, it's more mechanical than RF. Do you know what I mean? Because the mechanical piece needs more engineering and more work, especially with customers, because they're under pressure from a size and cost perspective. And it's really important for antennas. So yeah, glad to hear you say that.
Oh yeah, I mean, my favorite say about engineering, I don't know why it was said by Vincent van Gogh, but this is my favorite say about engineering, and it is, great things are done when a series of small things are put together well.
Oh yeah,
nice. And I mean, Vincent van Gogh is a painter. He doesn't put things together. He just basically paints on a piece of canvas. But why when you type on the web you find that he said it? I don't know. But I mean, you look at a Toyota car and you go check on the web. I mean, these things have 34,000 mechanical parts. They have 6,500 moving mechanical parts, from your doorknob to your door, to your engine, to your transmission, to everything that's moving. And then you put them together, and not a part is how do you say, not a single part is special, but you put them together and you end up with a gorgeous Lexus or a gorgeous, and that Toyota Camry, and this thing drives for 500,000 kilometers. That's for me engineering perfection. And the same thing I would say is engineering perfection is when you build a very complex system like a Dell laptop or a cell phone or a phase array. I mean, you can build a great phase array and the power supply is bad and you blow it up. You can build a great phase array and the antenna is bad, or the antenna is bad and it has a very high VSWR and blows the PA when it scans at a certain angle, as we all have seen. I mean, you have to do a lot of good work in a lot of different domains in order to get something that's beautiful and works really well.
Yeah, that's great. Yeah, I love that. But So look, what we like to do here towards the end of our show
Mhm.
is, for the guest to pick a technical topic, and no better than a professor from UCSD to give us a deep dive into a technical topic so our listeners can learn more about antennas. So
I mean, a technical topic one is, I would say there are kind of two ones. One is SATCOM. We started in my group by Gökhan Gültepe and Kevin Lowe. And from there, you realize that, in order to do SATCOM, you have to build 1,000 elements to 4,000 element arrays. Things become really large. And when things become really large and you start getting feedback. And sometimes things don't work. So you realize that, very high isolation in the PCB, very high, very good impedance match, no standing waves, feedback. You have all of this radiated power that would couple back into the PCB. So you need to pay incredible attention to isolation in the substrate and isolation in the PCB. Otherwise, you're either gonna get a lot of ripple, or ripple or suckouts, or you're gonna get oscillations. So that is one side. The other that I find is with wideband antennas. We use the Puma, we use a lot of wideband antennas lately at UCSD and at Extreme Waves. We're building a lot of wideband antennas. And you realize very quickly with wideband antennas that uh, you have to be careful, because you have wideband signals, wideband noise, wideband coupling, wideband VSWR. I mean, these things don't have very good VSWR when they scan to 60 degrees. They can, have a VSWR of 3 or 4. Oh, I mean, not 2 to 1, believe me, not 2 to 1. I mean, you can read the papers, especially at the edge. Edge effect starts mattering. And then you realize that when you're building wideband antenna arrays, and that you have to have extreme attention to details on everything. You have wideband gain, it can oscillate over wideband frequencies. You have wideband mismatch. You have wideband edge effects. Building a 6 to 18 gigahertz antenna, or 2 to 18 gigahertz antenna, it might work well at 12, but it might fall down at 18, or at 2, it's too small, the whole thing resonates, the whole box resonates at 2, because it becomes equal to lambda over 2, for
yeah,
example, at
and
2
it's like
gigahertz.
whack-a-mole because you
It-
fix one piece and then something else happens.
yeah.
Yeah.
So again, you go and say, how do you solve these things? We go to another say of mine, Marta Beck, which I think they used in a movie. And it is, what is it? It's, let's stop the interview here. I need to check it, please. It is, wait a second. It is, oh, yes, I remember. So let me go back now. So it is basically Marta Beck. And what Marta Beck has said is, how you do anything is how you do everything. And for me, this is also very, very important, because it tells you that, you have to pay attention to every little detail. And if you as a person is not the type that pays attention to detail, how you do anything is how you do everything, um, you are not going to succeed to build highly complex systems. So, even the screw counts, even the edge of the antenna counts, everything, how you do anything is how you do everything. Philosophically, it also means a lot. Is like, how do you behave at homes? How do you behave outside? How do you treat your families? How do you treat your friends? Who you are at home is who you are everywhere, and so on. But in design, it also means that, if you want something to work, you need to pay attention to every little step, especially when they are wideband complex systems.
Okay. Yeah, and
Yeah.
that's I think that's relevant for any engineering project, like you just talked about the car, right? It's like the attention to detail is essential for success, because we see you try and cut corners, you're going to pay for it at some stage later, right? That antenna is going to be installed somewhere in the world. And believe me, it can come back to bite you if the attention to detail was not paid to at every aspect
Yeah.
of it.
I mean, I finish by I say that engineering is a wonderful profession, and unfortunately, we are highly undervalued. Maybe not now. Maybe at least in California and the West Coast, they love us, but I feel in the rest of the world they are undervalued. But I mean, every time you take a plane and you land, you have to say, "Oh my God, thank you." I mean, I had 300,000 engineers at Airbus and at Rolls-Royce and Pratt & Whitney and at Boeing and Collins and Thales, and everybody worked together so that I can get this behemoth to fly and then land and everybody is safe. I mean, it is unbelievable attention to detail for it to work well. Or anytime you drive your car, or actually anytime you make a phone call. Oh my God. I mean, have no idea of how much work has done by Qualcomm and Apple and all the wireless LAN chips and the Ericsson and Nokia and the software and the fiber optics so that you can make a call, or you and I are talking to each other and so on and so forth. It's unbelievably complex with a lot of amazing engineering work in order for us to do something work so seamlessly and nicely in your hand, from a Dell laptop to a. So I really think engineers are underappreciated.
Yeah,
I really
no,
do.
well, I'm glad to hear you say that, because we often had that discussion in Cloudlast where we say, like, you've seen the price of some antennas in the marketplace, and you go like, look at all the complex work we're doing, and for cents, for cents
Yes.
on the dollar for a part. But so that's great. And one last question, Professor, advice for anybody that wants to get in. Like, sometimes we ask, how do we get in to the antenna industry? How do we get started? What's a good place to go to?
Well, start by taking antenna classes at universities, taking your EM class and taking at least an undergraduate antenna class. And then, I mean, if you just start by this and do well, you can interview and get a job. The other is that you get an internship. And the last thing I say is that you really don't understand something if you don't build it. If you don't build it. And sometimes I say, okay, I'm a professor, but where are the three things that I am, and I'm grateful for the university and so on, but Collins, Qualcomm, I worked at Qualcomm for 10 plus years as a consultant and embedded inside Qualcomm, and I really saw how they design chips and how they build everything and test everything and analyze everything, again, like Collins, in a very, very, methodological way in order to, get first time success or 1.5 times success. And you learn a lot from it. And the third is Keysight. I also worked, of course, as a visitor and a consultant at Keysight. And again, saw how you build these phenomenal instrumentation and how much work it goes in there. And in each time, what is that if you remain at your computer doing only analysis, you really miss. All of these companies, you have to go build it. And when you build it, you find mistakes, no matter how much you analyze, or you find omissions, and you go fix it, and then you build it again. And hopefully you can do it only in 1 or 1.5 iterations. You just fix few things. But for me, people say, why are your students so well trained? And I always say, because they build things. They build things, okay? Because we build stuff here. And it's a stuff to build, basically. Anything. And
Yeah.
so any advice I give to everybody is go build things, no matter what it is. Even if you take an old car and turn it apart and put it back together, you have built something. You have learned how to use your hand and you have built something. Go and build something with your hands, because just this concept of building something with your hand wires your brain differently and gives you a different Weltanschauung, a different view of how things are done, and a different respect of, of all of the things that you are doing. So yes, take some antenna classes, go build something. That's what you need to do.
Love it. That's great. Thanks so much for that. I love the passion. We can feel it coming out just for engineering, and that's the great advertisement for the antenna business right there, because people in antennas get to build stuff. It's not just, that's the opportunity that you get,
Yeah.
right? And that's why it's so rewarding. So
Okay.
thanks very much, Professor Gabriel Rebeiz. I'm delighted that we got the opportunity to speak. I'm Dermot O'Shea, host of the Antenna Podcast, and we'd like to thank you for your time.
Thank you. Thank you, Dermot.
Thank you.